they're basically all lost. It's not.
Good evening, everyone. So today we're going to do 12.5. We'll also get to 12.6. 12.5 is on lines and planes. So this is neat up until now when we deal with lines in two-dimensional space. We describe the line something like that, right? You're going to notice we describe it totally differently when you go to three-dimensional space, but it's not challenging at all. So I'm going to use this design right here. Y equals mx plus b. Yeah, that's great in two-dimensional space, but what about in three-dimensional space? How can you describe a line and all the points on a line? So we use vectors to do that. Isn't that cool? We actually use vectors. So I drew an image here, and this is the x-axis, the y-axis. We can then apply this to three-dimensional space using the vectors. Using the triangle law, I've got initial r here, r sub 0 or r naught. I got some vector A that's right on the line, everyone see that? And I got a vector just R. So let's just talk about R, because that would be like the tip of this. And using that, you could describe any point along this line. You can keep stemming like another R along this line. So I'm going to start out by writing the triangle law, and then we'll generate the equation of how we can deal with lines, and it'll be real easy. Let me start with this. Do you agree by the triangle law, that vector R sub 0 plus the vector A equals vector R, right? Mm-hmm. In fact, I'll write it as R equals this vector plus. This is going to allow us to create an equation of lines, not only for 2 space, but 3 space, using vectors. Vectors are so cool. All right, what I'm going to do is I'm going to think of a vector that's parallel to the line. That's the secret. I'm just going to tell you, how about a vector right here? Let's call it vector V. And I'm just going to put V right there. And let's just make a note, everyone, vector V is parallel to the line, okay?
Oh, which line?
To that line L right there.
Okay.
And I just drew a vector V, everyone. I put it off the origin. I could have put it anywhere, but I just wrote it on the board, and I said, let's just refer to some vector V that's parallel to the line. This is the secret to how we can deal with this scenario. And what we're doing is that we are deriving what would be the equation for a line, but not just 2 space. You can use it 2 space, but 3 space. Now, vector V and vector A are parallel. You all agree? So, can I replace vector A with vector V? I can, as long as I think of it as a scalar multiple of this. So what I'm going to do is I'm going to replace A with just vector V times some scalar multiple. Just a variable. And I'm going to use the variable t. Alright? I'm going to use the variable t. So I'm just going to be like, right here, how about V times t? And this is what we got. We can actually describe any line with a vector, where this right here will be just some point. I know it's written like a vector right here, but this will be some initial point on a line. Alright? I can take the t and just factor it out of this vector, and this vector v here will be the parallel vector. Boy, this is how we can describe any line. And if you want, what variable did I use? T. You can think of this as a vector equation like just R, if you want, you can call it R of t, as if everything's going to be in terms of the variable t. We'll always use t as our, you might say variable, let's call it a parameter. Let's call it a parameter because we already got what letters? X, Y, and what's the other letter? Z. So we'll X, Y, and Z, we'll say those are the variables representing points in three-dimensional space. We got a new letter T, and we'll just call that the parameter. That's our parameter. But we can describe any line like this. So all you'll need is a point on a line, just one point. I wrote initial, it could be any point on a line, and you need a parallel vector. All right, so we'll start with a simple example. The key is to describe any line in three-dimensional space from here on out. You need a point on a line, just one, but you also need a vector that is parallel to the line. Sound cool? So you might not think of it like this, although this is really what it is. This right here is just that initial point. You can think of it as like, you know, if it's the point 1, 2, 3, and you can write it as a vector if you want, because it's like it'd be the vector that went from there, from the point, from the origin, right? If you subtract 1, 2, 3 minus 0, 0, 0, tip minus tail, you can still get the what? 1, 2, 3.
Point vector.
So I'm going to keep this here, erase everything else, and let's play with this. So here's a point on a line. It's the point 1, 2, 3. This vector is parallel to your line. Four, 5, 6. And I want you to come up with the parametric equations of the line. We don't have to write it as a vector. All right? If you want, you can. For lines, you could say R of t is equals R sub 0 plus t times vector v parallel vector. But here's another way to think of it. The three parametric equations. So what I'm going to do, I'm going to come with this. These are called the parametric equations of the line. And there's not a typo here. There's not a typo here. I didn't say equation, I said parametric equations. So if we want to talk about describing that line, because we have this parameter t, we'll talk about what's x equal to, what's y equal to, and what's z equal to. Alright? I'll start by writing it as a vector, and then we can write it this way. So, I'm going to do this. Write it as a vector. And what would be the vector equation of the line? The vector equation of the line, I'll erase this. Is simply here. R of t equals initial point plus t times parallel vector. What's the initial point? 1, 2, 3. I'll write it as a vector. Right. Plus parameter t, and what's the parallel vector? 4, 5, 6. Put a big box around this. You gotta love this. We will not make this too complicated. Take all this out of the way. We can keep that up there. But this is the vector equation of that line. R of t equals 1, 2, 3 plus parameter t times 4, 5, 6. But can we combine these to make one vector? So let's do that. Meow. What would be in the x component? See, this is x, this is y, this is z. 1 plus 4t, or 4t plus 1. What's in this y component? 2 plus 5t. And the third component? 3 plus 6t. And that's the vector equation of the line. But I'm going to come back to this. A lot of times in our course, you may just want to write the three parametric equations of the line. Well then, what can I say x is equal to? X is equal to the what? 1 plus 14 the y is the 2 plus 5t, the z is the 3 plus 6t. If you're just asked to describe the line or come up with the line, everyone, of course, you can write it as a vector. If you're just like, I can come up with that line. But sometimes you'll notice the directions are just specific. And we'll say, write the parametric equations of the line. Then he wants you to write them like this. You can write them vertically, you can write them horizontally. If you write them horizontally, you might want to put commas between them, right? Because you'll have those three parametric equations of the line. But please, feel free to write these lines as a vector. All right, the next section after 12.6 is vector functions, right? And that's exactly how you describe a line with a vector function. It'll look something like this. There won't be any t-squareds in there, right? You start trying to describe some curve in three-dimensional space, okay, that's probably going to have maybe a t squared or a t cubed. With straight lines, just 1 plus 4t, 2 plus 5t, and 3 plus 6t. Most importantly, hidden in here, or hidden in here, where are the components that made the parallel vector? I wanted to make sure you know where that was. Those are the numbers in front of what parameter? 2. That's the parallel vector.
You also said that, right?
What's that?
You also said it on the question, that which are the parallel.
That's right. In this problem, they just gave it to you. So he's like, man, this one was easy. They gave us the parallel vector. They gave us the point on line. So let's go to another problem. And when you can write it as a vector, or you can write the parametric equations of a line. Can I erase this? But at least this is always going to be there, right? Throughout our whole course, the parallel vector goes in front of those t's. What goes here? Just the what?
Initial point.
The 1 point. Yeah, just the point. So you can write it like this, but you can also write it like, in this case if you prefer, or you can write it as a vector. But it's according to the directions, right? I know in this section you'll notice the directions, they'll say, find the parametric equations of the line. Then the next problem they go, find the vector equation of the line. And you write it either way. All right, so now, let's try another one. I'll erase all this. 1, 2, 5, 3, 4, 6. These are 2 points. Question? Find the line that represents those 2 points. Hey, be more specific. Okay, how about this? Find the parametric equations of a line that goes to these 2 points. So once again, what do I need when it comes to lines? I need a point, right?
Point and a vector.
And what kind of vector do I need?
Parallel.
So that's the challenge in this problem. So we're going to need you to brainstorm. I need a point on a line. Gosh, we got 2 of them, right? I always pick the first one. Is everyone okay with that? I always do. Up through chapter 16, they give you 2 points. Let's pick the first one. All right, 1, 2, 5. 1, 2, 5. Now I'm stuck. So I'm just thinking, let's draw a picture. Sometimes drawing a picture helps us figure this out. This is some point 1, 2, 5. This was some point 3, 4, 6. And I have to come up with the parametric equations of the line. You know, don't you?
Can't you just do tip minus tail and then multiply it by something?
She found a parallel vector. The challenge here was just to find that what? We just need the parallel vector. All they gave us was 2 points. And she says, well, if you just do tip minus tail, you will find a vector right on this line. In fact, parallel to the line, right?
Mm-hmm.
I mean, it's right on a line, but it's running in the same direction as this line here, parallel to the line. True? So if they give you 2 points, you can always use the vector tip minus tail between those 2 points. So what is, here, I'll put a vector right there. There it is. She says use that vector. That's your parallel vector. So cool. What's 3 minus 1? All right, so tip minus tail, 3 minus 1 is 2. 4 minus 2? 6 minus 5? 1. And I should have at least got some negatives in there, huh? Sorry about that. Negatives, we understand that. There's a parametric equation of the line. Can you write that as a vector? Certainly, that's the parametric. They ask for the parametric equations. I write them vertically, you can write them horizontally. And just put commas between them. What's the vector equation of a line? One each just R of t?
RT.
All right,
Then, one,
1,
so
2, 5 plus t times 2, 2, 1. Just remember, where is that parallel vector going? With the parameter, right? We derived it that way. Or what's another way? Most students like to write it as one x, y, and z component, like here. What's here? 1 plus 2t, 2 plus 2t, and what's the last part? 5 plus 2.
So the bottom part we call it like a vector equation of the line, and that one is parametric equation of the line, right?
Exactly. I'll repeat that. Very good. This is the vector equation of the line. Either one of these. Both of these are fine. These are the parametric equations of the line. Parametric because we're using this parameter t. Alright? We can always use the parameter t when describing lines. So throughout this whole course, you can imagine we got a lot of lines. Ooh, a beam of light, like going like this. So a lot of lines in this course, you can easily recognize them in later chapters because it won't have any t squareds, won't have any t cubes, it won't have any sine of t's or cosine of t's or e to the t's. It's just going to be like 1 minus 1t, 2 plus 8t, 5 plus 3t, 6 minus 4t, right? Or there could be a 0 in front of the t and then it'll just be the number, right? Very good. So they're easy to recognize. When you go, oh, that's just a line. Cool. Hey, there is one other way to describe lines besides saying the parametric equations on a line or the vector equation line. There's a third way. Like, how did we do this in algebra 2 back in high school and way back when? We just did something like this, right? And when there's a way you can write it like this, it looks kind of weird though, okay? Where you eliminate the parameter. And that's called the symmetric equations of lines. So we're going to do that with this one right here. This is the vector equation of the line. This is the parametric equations of the line. But can you write the symmetric equations of that same line? By the way, I do want to point out you won't do this nearly as often as those two. This is, you'll find you'll rarely do it this way. This would be the two ways you always describe a line. But there is a way we can do this. You go, what am I trying to do? I want to write it like this. I want to eliminate the parameter what? T. So to do this, because we want to eliminate t, yeah, and solve for t in each one. So let's do that, everyone. Let's solve for t in each one. Just go ahead, solve for t in each part. And that way we can just eliminate. All right, what's t equal to here? X, subtract the 1, then divide the what? All right, that equals 2, right? Put an equal sign. What's t equal to here? Y minus 2 over 2. Lastly,
Z minus 5.
over
1.
1, you don't put the 1 there. There it is. Symmetric equation line, you won't do this very often. All right, just put, you won't do this too often. In fact, this might be the last time we do it. Unless you work some of the problems out of that section. Most of the time, when it comes to calc, in terms of Calc 3, we'll be doing, you know, we're in chapter 12 right now, we start doing integrals and stuff. We're going to want to write things as vectors.
I got a
Okay,
question.
but there is a way to write it, eliminate the
So on
parameter.
the symmetric equation of the line, we don't use the angle bracket to note as a vector?
I know. No, we're really, what we did, Art, this is funny, we're writing it something like this. You know, like when we were y equal 2x plus 3, we eliminated this parameter t.
Gotcha.
The only thing is, there's 3 of them and it looks kind of weird, right? And that's why we won't do this too often. It's just another way to write it. The book in section 12.5, they will ask you to write some of the problems. Find the symmetric equations of the line. They just want you to eliminate the t. And that's what we did. Solve for t, eliminate the parameter, right? It just looks weird, doesn't it? Right, so there are only 2 of them? Yeah. So that's the way to do it. Okay. So great job, everyone. Hey, one more thing. Just describe the line, right? If they said line segment, doesn't a segment stop and start? So all we have to end, if they said, what was that last, what were the 2 points again? What was the first one?
1, 2,
125 and went to what?
6.
I just wanted to add this one thing. You go, what would I do if they said line segment that goes between these 2 points? Because the line segment starts and stops, right? Whereas the line we had before just goes on infinitely. True? All you have to do is make a little note after you did all this and just say, just take your t from, let's see, if I plug in 0, do I get the first point? Okay, where would I have to stop this? What t value would make it stop at this point? 1. That's all I have to add. So in this part right here, don't let it bug you. I just want to show this now. When does this become important, what I just did about a segment? Chapter 16. Because we're going to be doing integrals. We'll do doing something called a line integral. And you go, oh, what's going to be my limits of integration? You're going to have everything in terms of t. And you'll come back and go, oh, it's just going to be 0 to what? 1. To make you go from this point to this point, right? And you go, is it always going to be 0 to 1? If you set up your line this way, it will be. So be interested. That'll be at the end of our course.
I didn't get you. How do you get 0 and 1 for the t?
Oh, how'd you get this? So what we did was, we just looked at this to say, what values of t would give us these 2 points? Well, we noticed, heck, you put a 0 in for t, you get this point, right? But then she realized if you just plug in a 1 in here, and to say, what's 1 plus 2 times 1? 3. 2 plus 2 times 1.
4. Okay.
And 5 plus 1 is 6. So she
Okay.
realized that. But I wanted to point out, as long as you did this tip minus tail method to get the parallel vector, it would always be from 0 to 1. Every time. That's what would happen. And by the way, if you ever wanted to find like 5 more points on this line, what could you do? Just make up other t values, right? You say, hey, go find 5 more points on this line. Okay, use t equal to what? Negative 10. Use t equal to 15. Use t equal to 2. You could find infinite amount of points on this line by just making up values for that parameter. Does that make sense? And you got, there it is, that line going through 3-dimensional space.
Yeah.
So isn't this cool? So this is pretty big because we now have a way to describe a line in 3-dimensional space. So it's shocking that we didn't do what? Back in algebra class, they never taught it like this. And we just did 2-dimensional space. We did everything as what? Y equals mx plus b. We never wrote things like this in terms of lines, did we? But now it becomes, like essential that we do that. Cool. All right, so that's lines. Hey, we'll come back to these lines. We'll come back to these lines. That was good. I now want to talk about planes. So now we have a way to describe lines in 3-dimensional space, right? It's just going to be, put the point here, put the parallel vector here, and put t's here, right? And you get the parametric equations of the line, right? So I'll leave that up here in case we get different points here. Or I can just do what? You want the right, could this be our formula? Plus, 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 t, t, t. And what, I'm going to put an a, b, c in front. What's xo, yo? Xo and y are x naught, y naught, and z naught. This would be the initial point, right? A, B, C would be the vector that's what? Parallel. So x naught, y naught, z naught is just one point that you got on the line. The A, B, C is the, what kind of vector? Parallel vector. It must be parallel to the line, right? You can describe any line that way. Well, how about a plane? Well, let's just draw a plane. Plane like this. Here's a plane. Plane! To describe lines, we use a parallel vector and a point. To describe a plane, let's use a normal vector. What I mean by a normal vector, a vector that is perpendicular to the plane. So what if I have a normal vector? You can call that ABC. Alright? These are the components of the normal vector. And I'm just going to stick some 2 points in this plane. Here's a point. Alright, how about x, y, z? Will that work? Sure, there's a point in the plane. So we're deriving the equation of a plane. I'm just going to pick another point that's sitting in that plane. I don't know, how about like x naught, y naught, Z naught. How can we set up an equation of the plane? This is how we describe the equation of the plane. We got this normal vector, and we got these 2 points. Can you help me get a vector between these 2 points? What would you do? Tip minus tail, right? Tip minus tail, like x minus x naught. Y, if I did like from this point to this point, and I do a vector like that. Now, what do you know about 2 vectors that are perpendicular to each other? And the
Zero.
dot product.
0.
So we use the dot product repeatedly to describe equations of planes. Because what's going on here? It looks like this vector dot this vector equals what? That's how we do equations of planes. So here it is. Dot P equals 0. Dot product equals 0.
0, yeah.
One of the vectors is the ABC, right? What's the other vector? X minus x naught, y minus y naught, and z minus z naught. And what will this all equal to? It
0.
has to equal 0 because they're perpendicular, right? But let's write this bit. That looks weird. How about this? A times, this is what I'm going to leave up all class. A times x minus x naught plus b times y minus y naught plus c times z minus z naught. And I don't want you to forget this on the test. Is that it? Is that the equation of plane? Hold up. Equals what? Equals 0. Equals 0. Always, dot product equals 0. Okay. What's the ABC? With a line, it was the parallel vector. What is it with a plane? It's the,
Perpendicular.
yeah, there you go. You can call it the normal vector to the plane. You can talk about this is a vector that's orthogonal to the plane. You can call it the orthogonal vector, or if you can just say perpendicular. But you need that, and then you just need one simple point. So in a secant with a plane, you need a point on the plane, and you need a normal vector to the plane, which means you need some vector that is perpendicular to the plane. And you can always describe a plane. So on that note, everyone, here you go. Oh, here's my point. 1, 2, 3. Here's my perpendicular vector. Didn't I use 4, 5, 6 before? Okay, everyone. This vector is perpendicular to the plane. Perpendicular to plane is the vector, how about 7, 8, 9? Okay. Can you come up with the equation of the plane? This will be what? 7, 8, 9, x minus the what? 1, y minus the 2, z minus the, done. Now a lot of you might want to distribute that, and I think we should. Sound good? But can I leave an answer like this? Someone asked me to find the equation of a plane. Of course you can. That's my equation of the plane. But students do like to simplify it. What do we get here? 7x minus 7 plus 8y minus 16 plus 9z minus equals 0, or 7x plus 8y plus 9z equals, is it 50? Now that's better. You don't have to have it, leave it equal to 0, you can simplify it. How can I check to see if I did this right? Because I'm not going to screw up distributive property. What could I check? What would have to fit in this x, y, and z so it does equal 50? The point. You can plug that point right back in here, and it should all turn into what?
50.
7 plus 16, 23. 23 plus 27, you bet is 50. By the way, I do that all the time. I'm like, if I mess this up, I will just quickly take the point, plug it back into that equation to make sure it's working. Okay? So you can leave answers like this? Absolutely. Sometimes you may want to do this just because it looks a little nicer. Just don't forget that equals 0 if you do it like this, right? So we're always doing dot product to describe planes, true? But we need a normal vector and a what? A point?
So this one is called the equation to the plane.
The equation of a plane. This describes all points on this plane in three-dimensional space. Right? Now, how many points are on that plane?
3.
In terms of like, this plane right here, how many points are on it, like, theoretically? Infinite amount, right?
Yeah.
And so if you wanted to find a bunch, like, well, I could let that equal 0.
Uh-huh.
I could let that equal to 0, but then I'd have to solve for what?
Z.
50 divided 9. I could let this equal 1, this equal 1,000, then I'd have to solve for what? Z. Do you all agree? I mean, we could go all day long, just pick two numbers or two letters, then solve to see what the other, we can find points all day long. But that's what's so great about this. We have now described a plane in three-dimensional space. It could be flat, but it could be what? Nice and slanted. And we're about to get into 12.6, which is all the different surfaces. But now do you see what planes look like?
Yeah.
Most importantly, when you see planes, what do these numbers, we call them the coefficients, represent? The coefficients, when you just look at a plane, what do you know about this? They describe the components of the normal vector. That's what they describe. What's this 50? Just some number that falls on the right side, right? Who cares about that? But you know, you see the equation of a plane, that number, and that number had to be the what? The components of the perpendicular vector. Cool. It's interesting how often that can just help you out. You'll just go, you'll be in chapter 16 and go, man, I just wish I could come up with a normal vector to this thing, and you go, oh wait, it's 7, 8, 9. Right? There's other ways to get it, but you'll be like, oh, it'll just be 7, 8, 9. Cool. All right, well, let's try one of these. Well, can you come up with, erase all this. Leave this here. How do we describe equation of plane? A times plus B times plus C times equals 0, right? Or that's the normal vector. This is just some point on it. So now even from now on, I'll take this out. Because all we're saying is you just need that point, true? Hey, let's do another simple one. Make up a point.
3, 1, -2.
All right? To make up a vector.
4, 7, 3.
Now in this vector he made up is normal, is perpendicular to the plane. Give me the equation of the point. Find the equation of the plane where that's the vector that's perpendicular to the plane, that's the point on the plane. And we'll see the problems like this in a second. And by the way, you don't have to simplify it. So 4 times,
6 minus 3.
boom, plus
7 times.
y minus 1, plus
1 minus 1.
3 times,
Z plus 2
am I done?
equals 0.
You can tell by my face how many times Jin said left answers like, right? Oh, I forgot that. But there you go, done. Unless you want to go and simplify it. But that's fine. That describes the plane. That's the equation of the plane. Equation's got to have an equal sign, right? Okay. Well, we said that was too easy, right? Let's do a challenging one. I'll leave this up here for our notes. I want you to try this one. Great job on that. The points are, this is like 23 in a practice set. Which one's this like in a textbook? This is like number 31 from section 12.5. It's also like number 32 from textbook. Heck, I should do number 32. Nah, I'll make up points like this. Here's P. 0, 1, 2. Q. 2, 4, 4. R. 1, 0. I'll make this a 3. 3 points. 3 points on a plane. Can you find the equation of the one? All right. Let's start out. What do I need?
Normal.
I need a point on a plane. I got 3 of them. Does it matter which one I pick? All right, I'll use pick. Pick the first one. But now I'm stumped. Now here's a plane. Drawing a picture sometimes helps us out. Here's some plane. There's 3 points on it. Right? I've got one of the points, but I need a vector that does what?
It's normal.
Like that.
Oh,
Any
so
suggestions? Oh, I just heard it. He's got the idea. Get 2 vectors, so you're onto this. Outstanding, he gets first get 2 vectors in a plane from your points. Those 2 vectors will be in the plane. And then he says, take the cross product to those 2 vectors, because the cross product of 2 vectors is what? Perpendicular to the plane, right?
Mm-hmm.
Yep. And the markers, that helps just seeing it. You're like, he's saying get 2 vectors in a plane from those points. We can do that easily. And then when you cross these 2 vectors, give me that textbook. You cross these 2 vectors, you get a vector that is what? I need a third vector. Here. Bing. It's going to be perpendicular. And that's what we'll do. So first thing is, everyone, before we accidentally cross points, you can't cross points, we need vectors. You want to use PQ? What's PQ?
2, 3, 2.
2, 3, 2? Okay, what's PR? Tip minus tail. -1 and what? Now when we cross those, oh, here we go again.
No, PR is,
Did I mess up PR?
yeah, oh, no, it's equal. One.
We're good?
Mhm.
Hey, cross them. Remember how to do this? Wipe out the first column. Here you can put an IJK if it helps. And just put these vertical lines. We're getting the determinant of this matrix right here. So wipe out the first column. 3 times 1 minus 2 times -2. What's 3 minus -2? Hey, do the third component. Wipe out the third column.
Mhm.
What's -2? Subtract 3.
25.
Now remember, what do we do
Put
on this
negative,
middle component? We never do it in the other.
negative signs.
Negative, just do the same thing. Middle column, wipe it out. 2 times 1 minus 2 times 1, change the sign. So what's negative 2 minus 2? So negative of a 0 is just a what? 0. Hey, there's our normal vector. I always double check this. Because when with my eyes, I could have been looking at the wrong one. Column or something, let's double check this. Is this dot product with this 0? Is 5 plus 0 plus -5 0? Check the other one. Is 10 plus 0 plus -10 equal to 0?
Mhm.
Got it. So this is that normal vector. 5, 0, -5. Which point am I using? I just thought I used one. It doesn't matter which point you pick, right? Here's the equation of the plane. It's going to be 5 times x minus 0 plus 0 times
Why?
y minus the 1 plus,
-5 times.
I'll erase this now, -5 times,
Z minus 2.
all done? Equals 0. Or if you want to clean it up, what's it look like? Might look a lot better. 5x
Minus 5.
minus 5z, oh, it looks way prettier. What, that's a z. Plus 10 or minus 10?
Equals,
Equals -10?
yeah.
Do you want to even prove that if you want? I mean, 5, 5, and 10 or what? 5's a factor of 10. Divide a 5 on both sides? Okay. Or x minus z equals -2.
2.
Now, how can I check this?
Just plug the right number.
Like, I mean, before you turn in your test next week, check this point, but I wouldn't stop there. Check this
Okay.
point and check this point. All 3 work. There's no way you messed up. Now, when it's happened where a student had 2 of them work and the other one didn't, that means they made a slight error somewhere. And they spent like 45 minutes trying to find their error. You know, just kept doing some silly mistake over there. But I want is 1 minus 3 negative 2, check. Is 2 minus 4 negative 2, check. Is 0 minus 2, oh, this is the equation at point. Is that what it goes on? So that's probably as challenging as they get, really. You're like, oh, how do I get the, I got 3 points. You knew to find the cross product of 2 vectors. That was really good. Any questions on that? Hey, let's do a problem that involves planes and lines. All right?
We could have done it in dot products too, right? Because in dot product they're also 0. If they're 0, we could have done this one, right?
In terms of the,
Normal, find the normal, orthogonal.
between those 2 vectors?
Uh-huh.
Yeah, but remember what happened with this problem? We never had this first.
Okay, got it.
Yeah. But he had, what he realized with the 3 points,
Uh-huh.
he goes, all right, you have 3 points on, he goes, get 2 vectors in that plane and then cross them. Cool.
I understand, yeah.
And when I'm going to give a problem that's out of the textbook that relates planes and lines, this is the question. It's on page 824. Can you find a line to the point 106 and perpendicular to the plane x plus 3y plus z equals 5. Can you find a line to the point 106 and perpendicular plane x plus 3y plus z equals 5? Okay, anybody want to know what problem I just picked again? This was number 5 from the textbook, section 12.5. So this problem is involving lines and planes, right? But we are looking for a line. Let's go back to what we need. I need a point on a line. Do we have that?
Yeah.
Check. What kind of vector do I need? Because I need to find the line. So I need to find a vector that is
Parallel.
parallel to our line. I'm lost. I don't know what to do. I'm telling you what helps. Just make a little picture. Start looking at this and see what you got. All right, what? There's some plane here. What's the equation of the plane? I'll just write it. X plus what?
3y plus
Plus
z.
z equals 5. Okay. I'll find a line to some point. Okay, there's some line that's what? Just going like this. And it's got to be perpendicular. I'll put the line over here. There's the line. It's running what? I'll put it 90 degrees out here. There's the line, and there's some point on it. What is it? 106. But daggone it, if I could only find a vector that goes like that. Great eye. Ellen, he says, look carefully at this plane. Look what I'm looking for. We want a vector that runs parallel to that line. He says, hello, how are planes described? Planes are described by normal vectors. And he's looking at these numbers. Which one of these numbers in here represent that normal vector? The 1 and the 3 and the 1. The 1, you want to see that? Here, I'll put 90 degrees right here. The 1, 3, 1, who cares about the 5? The 1, 3, 1 represents the normal vector to the plane. Is that vector parallel to our line?
Mm-hmm.
We got it. Let's go fill it in. We get I read it vertically. Oh, want to write my parametric equations? You can write it as a vector if you want. X equals y equals 0, z equals, what's the point? 106, plus, 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 t, 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 and what's in front of these t's? A 1,
3,
a 3, and a 4. No, what's the last number?
1.
1. Coefficient of z. Parallel vector. You got it. These are the parametric equations of the line, by the way. Some of you may have written that as a vector. A vector equation of the line with parameter t. But it has to have that parameter. You don't have to always use t. You could use s, m. The book always uses t, so do I. Great job. A couple other things. This is problem number 45 from the textbook? Can I erase? Some with lines and planes. Or I can erase? Cool. This is number 45 from the textbook, something with lines and planes. This is what they wrote. They gave the parametric equations of a line. X equals 3 minus k, y equals 2 plus t. Remember, I'm writing this vertically. A lot of times it's written horizontally with commas between them. And z equals 5t. So I'm going to agree these are the parametric equations of a line.
Mm-hmm.
Here's the plane. So I'll just write line. Parametric equation of a line. Here's the plane equation. X minus 2y plus x minus y plus 2z equals 9. Okay. There's the line, there's the plane. The question, find the point where the line intersects the plane. The question again, this is number 45 out of the textbook. Find the point where the line intersects the plane. So once again, we're problem solving, going, how are we going to do this? So we're all thinking. I always draw a picture, it helps me start thinking about this, right? All right, there's the plane, right? There's that thing. And then the line maybe does what? At some point, the line's going to hit this plane. We're looking for the exact point that happens. But throughout all of mathematics, have you noticed a common theme when it comes to the word intersection? Right before your class, I was teaching Calc 2. We talked about two curves intersecting. We talked about, the substitution rule. Take one variable from one equation, substitute in the other, and you can find where they intersect. So if we're trying to find where a line intersects a plane, then this definitely involves some kind of substitution method. Any suggestions?
Yeah, so x, replace them like 3 minus t,
Take this, put it there,
Uh-huh.
substitute it. Take this, substitute it where?
y.
There. Take this, substitute there. Whoop, let me get pointing to that z. And then we're going to solve for what letter? Man, you're good. 3 minus t minus, be careful of the sugar probably, 2 plus t plus 2 times 5t equals 9. Great idea. All right, what is all that? Minus t minus 2 minus t plus 10t equals 9. Like terms?
T,
3 minus 2 is
1.
1 minus 1 plus 8t equals 9. Okay, you're kidding me. Was this easy? And when I take 1, I subtract 9. What's the t?
1.
Okay. Maybe a little bit too easy. T is what? Hey, don't leave the answer like that. One more step. They said find the point where the line intersects the plane. What do I do with this? Put it right back in the parametric equation. You'll get your x, y, and z point. Let's do that. What is that real point? So when it's at t equal to 1, so I'll say it's at t equal to 1.
3
The
minus
point
1.
is 2, 3, and 5. That's the point. That's the answer. That's the point. Hey, I apologize that, highlight this in your notes. I didn't put one of these on the practice set. I should have. It's a good problem. So would you just make a note of that? Yeah, it's a good problem. Just because it really involves, we're thinking about lines and planes, and we took an old math skill of intersection. How do we find where two things intersect each other? But I didn't have that on the practice set. But great problem. You know what to do. Cool. Hey, a couple more things before we go on to 12.6, which is really cool with the other surfaces, is if I give you two equations of planes, how can we tell whether or not they're parallel to each other? Someone? These are two equations of a plane. All right. How can we tell whether these planes are parallel or perpendicular or neither. So let me look at this one. All right, x plus 4y minus 3z equals -1. Does that look like the equation of a plane? Right? That's a 1. X plus 4y minus 3z equals 1. The other plane equation is -3x plus 6y plus 7z equals 0. The question, are these planes